Hi everyone. Today the speaker is Vladimir Itskov from Penn State, and he's going to tell us about directed complexes, sequence dimension, and inverting a neural network.
Okay, hello everybody. So thank you for having me here. So let me give you probably overly ambitious overview of what I will be saying. So there is a bigger picture which some of its pieces won't end up in my talk. And there is geometry and there is topology. So the topology is on the right, geometry is on the left, and there is a set of problems that I loosely call convex sensing, and we'll consider one very concrete example, the monotone rank, but there are more examples of these types of problems. And they're related. The way these problems can be solved is via topology. So we'll talk about directed complexes and multi-filtrations of simplicial complexes, namely Dowker complexes. So this is just a very broad overview. And these problems, before I go on, these problems come from my perspective, they naturally arise in neuroscience. So I will mention two situations where they arise, and one is feed-forward networks, and the other I will, there is this question which I will elaborate later on. We call what is the dimension of a space of smells, but I will explain this later. All right. So let me explain the very basic neuroscience motivation for convex sensing. So this is a classical example from neuroscience literature. In fact, the major findings that I'm going to show on the slide, they're very old. They come from 80s, and at some point they even received Nobel Prize. So there is a set of cells in mammalian brain called place cells. They are located in hippocampus. It's an area in the brain, and they act in a very weird but beautiful way. So if you record from the cells and let the animal roam, say, rectangular room, this blue square you see here is just the actual physical location of the animal, then you would notice that the cell is active in some relatively small convex subset of this room. So a different cell would be active in a different convex region and so forth. And they are only approximately convex, of course, as you can see from these figures, but nonetheless, in a good approximation, you can treat them as convex. So, of course, this needs more elaboration. So let me give a couple of formal definitions. A receptive field of a neuron is just a function from some space. Call it X. In this situation, X would be literally this rectangle in two-dimensional space to real numbers. And these, what you see here is exactly the values of this function. So this is the color map of this function, right? And as is clear from this picture, hippocampal receptive fields are approximately quasi-concave. So what do I mean by this? Well, we can threshold this function at particular level theta, and the preimage of this is convex. So let me, maybe I should give more formal definition. So a function in Euclidean space is quasi-convex if the sublevel sets are, all the sublevel sets are convex. And of course, the usual notion of convex function implies quasi-convexity, but not the other way around, because here you see a nice example of quasi-convex function on just in one variable, and is obviously quasi-convex, but it's not convex, as you can see from here. And another important fact is that if you apply monotone increasing function to quasi-convex function, you again get quasi-convex function. So the quasi-convex functions are invariant under monotone transformation. All right. So again, as you saw in that one example, coming from neuroscience, there are classes of cells in the brain that respond to whatever stimuli spaces that we observe in a nice quasi-convex manner. And it's actually very common. It's not a unique property of hippocampal place cells. There are many other classes of neurons in the brain that behave in similar manner. I won't talk much about it, but here is a natural question. So if we do not actually know what these represented stimuli are. And the receptive fields can we still, but can measure neuronal responses, can we still figure out the space? So the reason for asking this question is very straightforward, because the example I showed you is very well studied, but in most cases, people don't really understand how various regions in the brain process information. So if you make an assumption that the receptive fields are still quasi-convex, then it's natural to try to understand the underlying space via activity alone, right? So that's a highly natural question. And this is very vague question, so I can make it more specific. So can we tell the dimension of the underlying space? In fact, this is what I'm going to be talking about today. Can we figure out topological features of the space? And ironically, this is much easier. And can we also figure out the convex geometry of the space? I never told you what I mean by convex geometry, but all I should say, this is much harder question. So you won't see much of this in this talk. Okay. So first of all, I should say the dimension inference is an ill-posed problem. Let me become more concrete. So let's say somebody gives us a matrix that is sampling a space from a points by quasi-convex function. So here, all we know is the left-hand side. And here, these functions fi's are unknown. And neither are the points. We assume, for a moment, let's assume they just live in Euclidean space. But what we know is that fi's are quasi-convex. And here is a natural question. Can we still find an embedding of this matrix into Euclidean space? What do I mean by this? Can we find points in Euclidean space xa in Rd? And Fi is such that this matrix comes from sampling functions at the set of points. Well, here is a big warning sign. For this to work properly, one needs to either have a good sampling of points or more assumptions on the functions Fi. So let me explain why this is necessary. So first, a big warning, this problem as is ill-posed. Namely, I claim that we can always embed any matrix into just two-dimensional space. And I don't have a cute picture for this, but imagine embedding points on just a boundary of a circle in R2. And if you're bored with the rest of my talk, which will turn very topological, you would see that you can play it directly, and so you can actually find these functions by cutting chords on a circle. So this is not hard, but of course this is cheating. Why? Because if you place points on a convex hull of somebody, then this is very special sampling. So normally, if you sampled any space, you want to sample the interior, of course. So you can't just place everything on the boundary, and therefore the condition of well sampling the space should be one of the main conditions, of course. So, like I said, we need two constraints. We need either have assumption of good sampling or a different assumption placed on the functions that we use. So, so far I just said quasi-convex, but they can be more restricted, and I will talk more about this. So now I will finally get to talk about directed complexes. Before I go on, I should notice that if we somebody handed us a matrix and told us that these functions are quasi-convex, if we apply monotone transformation to this function, we get another similarly quasi-convex function. Therefore, we should quotient by monotone transformations. What it means is that we need to consider quotient of set of all matrices by set of all monotone transformations. And I claim that this is exactly the directed complexes. First, let me explain what directed complexes are, and then I will come back to this point. So what are the directed complexes? Let's say V is just a finite set of vertices, and a sequence in V is a simplex but with an extra structure. It's given a total order. So we consider tuple with ordering. And again, the vertices vi do not repeat. And which means v1, v2 is not equal to v2, v1, right? So we care about orderings. And the set of all sequences in V, of course, is a poset by inclusion. So it's the usual thing with standard simplicial complexes, only now we take the ordering of vertices very seriously. And instead of subset, we have a subsequence. And the directed complex is just a poset of sequences closed under inclusion. So it's complete analogy with the usual abstract simplicial complex. And as you can imagine, these objects actually have very similar topological gadgets as the usual abstract simplicial complexes. So there are geometric representations. You can glue simplices with ordered vertices together to obtain something nicely embedded in Euclidean space. There is a notion of homotopy equivalence. There is a very simple notion of homology and cohomology. And the formulas are pretty much the same, only now you take the ordering of vertices into the account. So I won't write it on my slides. So these are the same topological gadgets, but now we have to keep in mind that the most simple object, let's say the set of all sequences, is no longer contractible. Why is that? The set of all possible sequences would be the maximal possible sequences would be all permutations, right? So instead of one simplex, we have n factorial simplices, and as you can imagine, this won't be easily contractible because of the relations between different sequences. In fact, later I will tell you there is exact theorem that relates to this. Okay, so now how do these directed complexes relate to geometry? So let's consider the following simple problem. Let's embed a set of sequences or directed complex into Euclidean space in the following manner. Somebody gave us a set of sequences, and we want to come up with representation of vertices in actual Euclidean space, such that for every sequence, they exist a vector W, such that the ordering inside the sequence is exactly the ordering of the projection of these points on the line defined by W. Is it clear?
Yeah.
Maybe you guys should
a question. Do you also want to have the property that any W gives such a sequence in your complex?
No. It's the other way around. So
no, I understand, but so every sequence in your complex has to have a corresponding W, but not every W in Euclidean space determines such a sequence. Is that right?
No. Here, all I ask is that there exists W such that it
That's right. So I'm allowed to have W that give me different sequences that are not included in my complex.
Yes.
Yeah, okay.
For example, you could have just literally one sequence. Obviously, and if I place points like this, of course I would realize the sequence, but that would be completely different sequence.
Right. Thanks.
So there is a different notion that I will define later that will probably emulate what you were suggesting, but it will be later. Okay, so now let's just define monotone rank of directed complex as minimal possible dimension of such embedding. It's actually not hard to see that you cannot, your dimension cannot be completely arbitrary. For example, if your directed complex consists of just literally one sequence, you can embed it on just real line, so that your embedding dimension will be 1, right? You literally place it on the line. But if your directed complex has more than a sequence and maybe it's reverse, you cannot place it on the line, no matter how hard you try, obviously. It's obvious fact, right? So clearly there should be constraints on the dimension in which you embed your directed complex. All right. And okay, so now I'm going to come a little bit back and again say that this problem, which I described, the embedding dimension of a directed complex, is actually very natural and comes from very concrete question about neural networks. So there will be this quick intermission about neural networks, and I will come back to the directed complexes and discuss what it means in topological terms. So why this embedding dimension of directed complex? So there is this very simple-minded question in neural networks. And if you don't know what neural networks, don't worry. You can think of neural network as just you have input variables, call them xi, and output variables, call them ya. And neural network is literally this formula. What this says is that you apply affine function to variables xi and pass them through monotone increasing nonlinearity phi I. And there is a very simple-minded question. Assume that we know the activity of the output layer, but we don't know anything else about this neural network. Can we estimate the question? Can we use the output to tell the size of the input layer? And it sounds like a very simple problem, but ironically, it doesn't have a very straightforward answer. And let me explain why. So what does this account to? We have, if we know output of this, sorry, what does this amount to? If we have the output of this network, we can think of this as just a set of vectors. And we want to decompose M as this nonlinear factorization, where phi is the vector of this monotone functions phi, and this is just matrix multiplication, right? So this is the formula. And all we know is M. We don't know anything about the right-hand side other than monotonicity of phi I. And as you can imagine, this, if you think a little bit, this becomes exactly this problem, right? So why? Because monotone functions define an ordering of elements in each row of the matrix M. Right? So now this problem of the embedding directed complex becomes this problem. Let me explain how this works. So every matrix has a directed complex associated to this. How do I define directed complex associated to a matrix? Very simple. I take a matrix. For each row, there is a certain total ordering on the elements of this row. And by the way, I assume that each row has non-repeating elements. So this is why we just cut out singular set. Can be done without this assumption, but it just makes everybody's life easier. So I will stick to this constraint. Okay, so each row has total ordering of the elements, so it gives us a particular sequence. So now we collect sequences for all rows and obtain so-called pure directed complex, right? So they're all in the same dimension. The top elements, the top simplices are all in the same dimension. So, and this D of M, the minimal number of neurons you need in the previous layer of in the input layer of the neural network is exactly the same as monotone rank according to this definition. Monotone rank of directed complex obtained from this matrix. All right. So here is just to make sure that everybody is on the same page. Very concrete example. So somebody gave me this matrix, and from this matrix, I can derive this three sequences, right? This is the ordering of the entries of the in each row of this matrix. So, and these three sequences generate the directed complex. All right. So Of course, there is geometry associated to this. So first of all, the way to think about it is the embedding problem can be processed as there is a hyperplane going from negative infinity to positive infinity according to this vector W over here. So again, each sequence is simply the sequence in which this hyperplane meets the point. And by the way, this function as a function of x is quasiconvex. It's almost too transparent. Why? Because the sublevel set would be half space, so obviously it is a convex set. But this is a rather special case of being a quasi-convex function. So the equation of the embedding dimension of the directed complex fits into this more general framework of convex sensing, but it's a bit too special. And some simple facts about monotone rank. So first, of course, monotone rank is determined by ordering each row of a matrix. And also, monotone rank should be smaller or equal than the usual rank. That's no surprise, because if we just dropped phi, that would be the usual rank of the matrix. And there are combinatorial constraints that guarantee that that rank is bounded from below. So let me, and these of course come from convex geometry. So let me explain those a little bit. So if we the truth is that as many there are theorems in convex geometry, as many constraints on monotone rank I can think of. But let me just give you one, just to give you a flavor. So there is a bound from Radon theorem, for example. So the explanation is very simple. So if we have two different vertices, and if we have a sequence of these vertices v1, v2, and so forth, vn, such that these vertices are separated by a hyperplane. Remember from this picture, if there is a hyperplane that separates two sets of vertices, if there is a sequence of vertices and we put some boundary in between the sequence, there is a hyperplane that will separate them, right? So in particular, that means that the convex halves don't intersect. And recall the usual Radon theorem that says that any set of d plus 2 points in RD can be partitioned into two disjoint sets whose convex halves do intersect. So this is an illustration in d equals 2 case. So, and what it means is that if our set of sequences allows all partitions of the vertex set, then the monotone rank is bounded by n-2. So this is one of the constraints. And for example, the matrix that I showed you before, this implies that the monotone rank is exactly 3, not 2. Okay, so this sounds like complete dead end. From geometric perspective, one can try to prove very subtle theorems about convex geometry. This is just the simplest possible example. But that does not give you any tool in estimating the embedding dimension. However, here the topology comes to the rescue. So it turns out that with some reasonable assumptions, one can use topological tools to actually estimate dimension with good accuracy. So now I will abruptly switch gears, and we'll start talking about topological properties. But disclosure, there will be two different situations that I will discuss. One is the good sampling of functions, and the other is good sampling of points. And the topological tools are somewhat different. So what do I mean good sampling of functions? So if you measure a space via just points with functions, you have two extreme situations. You can measure it with many functions. In the case of monotone rank, that would be just having many hyperplanes, like Henry suggested. Or you could alternatively just have many points but very few functions. So first, let me consider this good sampling of functions case. So, and the first thing that is natural to do is to consider the limit of many enough functions. So what do I mean by this? Let's say we just have a cloud point in point cloud in Euclidean space. We have n points, and one can define the so-called linear complex of sequences in for this particular set of points in RD as sequences coming from all linear functions, this affine space. So, and I believe this is what Henry was suggesting in your earlier question.
That's
Am
right.
I right?
Yeah.
So this is the limiting case. So if you want to consider all possible functions, then you want to stick to this complex. All right. And ironically, it was known for quite some time in different guys. So in 1967, Thomas Cover, who coincidentally was the first person to study geometry of neural networks, computed the number of sequences in such complex. Well, he didn't know it was a directed complex, obviously, but he was just counting the sequences, and he found this nice recurrent formula for the sequences. And I don't write, and of course one can write it explicitly, but it's monstrous formula that using Stirling numbers that nobody really wants to see in their life. So I leave this cute recurrence relation instead. Okay, so now, and this is pretty much what is known about this complex. So now, here is a question: can we read off the dimension from the topology of this directed complex? And the answer is actually yes. So one can prove that if somebody gave you the cloud of points in d-dimensional space, if n points, there is this complex of linear sequences, then the reduced homology of this vanishes until dimension d-1. And moreover, you can compute Euler characteristic of these complexes, and it turns out it's the same as the Euler characteristic of wedge of n-1 d-dimensional spheres. However, there is some catch. So here the dimension, sorry, not the dimension, but rather the number of points n needs to be sufficiently large. So here there is some condition on the number of n of points. So if there are too few points, then it's actually not true. This part, that Euler characteristic is just Euler characteristic of n-1, wedge of n-1 d-dimensional spheres. So first, let me explain why this is true. So there are two parts to the statement. One is this, the vanishing of low-dimensional homology, and the other is that Euler characteristic is that one of the wedge of -1 d-dimensional spheres. So there is an earlier work on so-called complex of injective words, which was done by combinatorialists, and that was most of this work was done in the 80s. And complex of injective words is a very simple object. It's just a complex of all possible sequences, which is all possible permutations. And this object comes up in the representation theory a lot, as a matter of fact. And what these people proved, so the original result was by Parma, by a different person, but these two people, Michel Wachs and Björner, proved that this complex is shellable, and moreover, it is homotopy equivalent to wedge of n-1 dimensional spheres, where n is the number of vertices. And this is not a typo; it is called the number of derangements, and there is a combinatorial formula. All right. So now, if you look back in our directed complex, one can realize that one can realize that the sequences up to length d minus 1 rather are sequences up to length d, not d minus 1, up to length d, they're all realizable. It's a simple convex geometry, and therefore the low dimensional homology for the complex of linear functions will be the same as the one for the complex of injective words, and thus this formula with vanishing works. So the early characteristic argument is a lot more complicated, so I won't give you, but it boils down to some nasty combinatorics of the just basically boils down to a lot of counting arguments. And the crazy thing is that the combinatorics of the complex of linear sequences actually does depend on how you arrange these points in RT. Because, for example, you can arrange them all on convex hull, or you can arrange them that some points lie in convex hull of the other points. And one can easily prove that they're not combinatorially isomorphic. But nonetheless, the topological properties are preserved. So somehow the homotopy type is preserved. And we have this conjecture that we also tried to prove, but we failed. So far, the status of the conjecture. So the conjecture basically strengthens the previous theorem and says that, in fact, we believe the homotopy type of this is the same as homotopy type of wedge of spheres, but slightly weaker conjecture is just the homology is the same. And the reason why we believe this is not only the theorems we proved, but also this object is highly computable. One can compute this using computational tools. In fact, we have a package that does just that. We computed all computationally feasible examples, and everywhere it was holding. So, but that's of course not. Okay. So now,
can I interrupt to ask a question?
Yeah.
What's the spirit of your Euler characteristic proof? Are you sort of counting simplices and?
Yeah, it's straight combinatorics, right? So ironically, there is no topology here, even though we, of course, in the end we pull this topological claim. But technically, there is no topology involved because you can compute we just count the dimensions of the chain. The appropriate chains. That's it.
But it's impressive that you're able to do this for all x in general position, because as you said, they're not combinatorially the same as you vary x.
Yes, so, they're not combinatorially the same, but the key argument here is that this Kova theorem that I showed you in the very beginning, he basically resolved this question once and for all, that the combinatorics is different, but the number of sequences is the same.
I see.
So this is still the key. This very old theorem by Thomas Kova is still the key, because among other things, he proved that even though combinatorics is indeed different, the number of sequences is the same.
Thanks.
Yeah, and this is why it looks like a miracle, but it's actually not a miracle at all, right? So it's a very natural statement. Okay, so all right. So now, question: what happens when sequences are not completely sampled? Because if you noticed, I did some bait and switch in a way, because I told you, okay, let's consider the case when we sampled enough functions, and then I said, let's just say we sampled all functions, but number of all functions is exactly this number of sequences that Thomas Kova derived, and like I said, it's this nasty combination of certain numbers which grows very badly. It grows like binomial coefficients. So there is no hope that any reasonable data set would have sampled all linear functions. However, it turns out that there is this weird phenomenon that we discovered experimentally, that even if we grossly if one grossly undersampled the set of functions, you can still use the same theorem to correctly infer the dimension, simply by vanishing by the homology vanishing argument, right? Because one way to obviously infer the dimension of a wedge of spheres is compute homology and see which one is the first non-vanishing homology, right? Very straightforward. And this is what one can do. And then this is the estimator for dimension. And it turns out that if you just, this is a simple plot from computational experiment, you have number of sequences versus probability of inferring the dimension correctly. And what you're supposed to read from this plot, for low enough dimension, you can still use this theorem to infer dimension correctly, even if you grossly undersampled the actual functions. Because this theoretical number of possible sequences is way off the charts. It can be shown on this plot, but it's very high. So it's not, it couldn't be shown on this plot because it would be many thousands here. And nonetheless, for a relatively small number of sequences, the probability of giving the right answer quickly converges to 1. And we don't understand this phenomenon. We believe there is some really neat convex geometry that goes on that needs to be done by somebody else, and so we leave this observation as that. Right? So it's for some more geometrically inclined person to figure it out. So now, what happens if instead of many functions, you have many points? Oops, how many minutes do I have? Like 13? Henry?
Yes, so you have about 13 minutes, yep.
Yeah, so here it turns out that there is a different topological object gadget in play, which is related to directed complex, but I will pretend that it does not matter, and I will explain it in more elementary terms. So if somebody gave you a matrix, let's say this is your matrix, and you set for each row, you just set a particular threshold, theta, and you do this very simple-minded procedure. You ask if the value of the matrix is smaller than the threshold corresponds to this row. You get a binary matrix, right? And then for each column of this binary matrix, you assign a simplex in the vertex set, where your vertices are now the rows, and they have meaning of functions. So note this is in a way transpose of picture with the directed complex. And of course, for different set of thresholds, you would derive a different complex. So definition Dowker complex associated to the set of sequences. Set of thresholds is the simplicial complex obtained from interpreting each column of this binary matrix as a simplex, right? And of course, it is actually a multi-filtration. Why? Because if one set of thresholds is always larger than the other, then the appropriate complex is a sum complex. So what we have is lattice of thresholds and the appropriate functor, if you like, into the simplicial complexes. And the same procedure, just in more abstract terms, can be applied to any directed complex as a matter of fact. So any directed complex generates, any pure directed complex generates multi-filtration of Dowker complexes. So why is it? And a fun fact, the reason why these are called Dowker complexes is this fun theorem that says that if somebody gives you a binary matrix, and now you can also compute the transpose, of course, and then it turns out the Dowker complex associated with the binary matrix is homotopy equivalent to Dowker complex associated with the transpose. So in terms of our picture, that means that if you transpose the meaning of functions versus the points, you get a homotopy equivalent object. Kind of fun. And the crazy thing, nobody really found a good use for this theorem, even though this is what's almost 70 years old. But bear with me. So again, this is the reason why I call these complexes Dowker complexes. So now, how is it related to our question? It turns out that it's very simple and almost too natural. So again, reminder that if you start with this neural network picture, right? So then what we want is if you compute Dowker complex of this, what does it mean? It means that we ask a question about these inequalities. So if we write these inequalities, the fun fact about monotone and strictly increasing functions, one can invert them in an inequality and write this as that. And of course, you immediately recognize this is nothing more than just an equation for half space, right? So translation, this inequality holds if and only if the appropriate point labeled by index A lies on the positive side of this hyperplane HI plus. And moreover, under certain condition, which I will explain in a second, the chambers of this hyperplane arrangement actually correspond to the facets of the nerve, and the Dowker complex is literally the nerve of this cover. So Dowker complex can be understood as Dowker complex for this matrix can be understood as a nerve of a cover by positive half spaces, and in particular, the Dowker complex should be homotopy equivalent to this union. It's just a simple nerve lemma. And of course, I hit some conditions. So the condition of enough sampling means that if we consider this cover by half spaces, there are privileged chambers that correspond to the facets of the nerve complex. And the enough sampling condition means that for each such chamber, there is at least one sampling point. All right? So, of course, this is rather a strong assumption, but bear with me, it turns out that it can be circumvented. So, in particular, the corollary of this little lemma implies that Dowker complex, if we started with this neural network picture, then the Dowker complex should be homotopy equivalent to RD minus some polyhedron, right? And with some simple geometric manipulation, you can turn it into a polytope, and therefore it will be just d minus one dimensional sphere, which is of course very simple to detect. But here is a catch. In order for this to be true, one needs this condition, which generally is not satisfied. So, can we? Here is a natural question: can we still infer the dimension even when this condition is not satisfied, when the space is undersampled? And surprisingly, the answer is yes. So let me explain. And here I have to go a bit quicker because I have limited time. So let me explain it in a more fast-forward manner. So now, one thing, of course, I have mentioned is that these thresholds are flexible. We can choose filtration of these thresholds any way we like. And given an increasing sequence of thresholds, there is appropriate filtration of Dowker complexes. And here I'm cheating. Instead of having multi-filtration, I just choose a particular path in this multi-filtration to get a single filtration, right? And once I've done that, I can play the usual games with persistent homology, circumventing the difficulty of having multi-filtration altogether. And now, this is very standard setup for most TDA people. So we have filtration of simplicial complexes, we have homomorphisms in homology, we have persistent intervals, we have so-called Betti curves, which are just dimensions of the homology groups. And I will just illustrate everything with Betti curves because it's in a way more visual in this case. But there is, of course, analogous gadget on the level of persistent intervals. So now, what I mentioned is that one can choose these filtrations of the thresholds very judiciously. And to make very long story short, one can average over these choices and obtain so-called average Betti curves. Again, these would be each of these curves is the dimension of the appropriate homology group for Dowker complex. And we also average it over the choices of thresholds. And it turns out that one can easily infer a dimension using the shape of these Betti curves. So there are actually two ways to do it. So the first way, if you know that your dimension is pretty low, so you can easily compute the homology group. For example, here this is Betti 1, this is Betti 2, Betti 3, and so forth. And here the true monotone rank was equal to 2. So you can see that this is a signature of long persistent cycle in dimension 1. And this is just noise terms, right? So these are noisy cycles in dimension 2 and 3. And similarly here, you can easily see the signature. So for here, the monotone rank was 3. Therefore, the sphere we are supposed to observe would be S2. And indeed, in Betti 2 has this nice plateau, which is indicative of long persistent cycles. And these are again transients, so it's very easy to detect the dimension. But there is more difficulty here. If you know that your dimension is relatively high, let's say 7, and your number of vertices is, I don't know, 1000, then the dirty truth about topological data analysis is that higher order homology groups are pretty incomputable for high enough k. So this Betti numbers, beta k, are not feasible to compute if your complex is very large. So how is nonetheless, I claim that it's still possible to infer the dimension. How is it possible? It turns out that yes, the relevant dimensions that we want to look at to check for persistent cycles are uncomputable. But it turns out that even for lower dimensions, this is Betti 1, Betti 2, Betti 3, Betti 4, and so forth, there is a nice stratification by dimension of the height of the Betti curve. So what you're supposed to read from this plot is this number 3, 5, 7, 10, 15, 20 are just different true dimensions. And this is how the Betti curves nicely stratify. So you can read the dimension from the heights of Betti curves, even though this result with the sphere is pretty much uncheckable due to the humongous cost of computation you need to do to compute, I don't know, Betti 15 in a complex with 1000 vertices. Because you won't even fit the problem into a computer. So the idea to make this story short, so this is also computable, and this phenomenon of certification, there is so far this is experimental results. So someone needs to prove the probabilistic estimates for when this is reliable and when this is not, but it's a lot of work. So okay, so I have like 2 minutes. So now let me just tell you one application that I mentioned at the very beginning. So now if one buys into this convex sensing picture that neurons have convex receptive fields, one can do really fun things. One can take neural activity data from a system that is not very well understood. And this system is called olfaction. This is a sense of smells. And what you see here is literally the matrix of responses of different types of neurons in rodent nose to various orders. So this is exactly this giant rectangular matrix. And one can ask this seemingly naive question, okay, if we believe in this convex sensing, what is the lowest dimension we can embed this matrix? Okay, so translation, if you believe that your receptive fields are quasi-convex, can we estimate the dimension of the sense of smell? And ironically, this is a controversial subject in neuroscience because nobody knows what it is and nobody has a straightforward approach at telling the dimension of space, let alone even defining what this space really means. So, but nonetheless, we can apply our methods and infer an estimate on the dimension of the space. And it's unfortunately it's probabilistic because here, like I said, you have at some point you have to deal with probabilities, and one can derive the particular p-values, if you like, that is the probability of making an error. And nonetheless, with very high probability, we see that in this kind of data, we have dimension between 4 and 6. That's the best we can do. Okay, and I should stop here. So just a quick summary. So convex sensing problems can be best understood in terms of directed complexes. And again, directed complexes are slight generalization of the usual abstract simplicial complexes, and they have somewhat different or very similar properties. And natural questions about feed-forward networks can be restated in terms of nonlinear matrix factorization monotone rank. And exact bounds on the monotone rank are still poorly understood because it requires a very fine understanding of convex geometry, but nonetheless, it can monotone rank can be estimated with high precision using topological tools. And that's it. And these are 3 people who did a lot of hard work related to the slides. And I will stop here and let you ask questions.
Okay, great. So questions. Okay, so Vladimir, I remember that you mentioned like this data set a while ago already. Are there any other sort of data sets that would be good candidates like for?
Yes, so this data set is fly olfaction. So now I actually collaborate with people who do rodents, and we playing with the data a lot. And the similar style analysis was done in hippocampus already. We have one paper published on that. And the reason why I really like olfaction, this context, is that the question of dimension is is not random there, because if you ask what's the dimension, I don't know, of motor response, it's kind of silly question. Nobody needs to know. But if somebody asks, okay, can you define a sensible coordinate system in a factory space, it's actually a question people really care about, because the space of smells is very badly understood currently. Clearly it's some chemical features of the molecules, but how is it organized, nobody knows.
I had a question: do fractional dimensions ever come up in neuroscience, or is it more that if you don't even know whether it's 4 or 8, asking for a fractional dimension is asking for something a little too precise?
Yes, I think the question of representing something akin to Euclidean space is very appealing to neuroscientists. But these more abstract questions of fractional dimension, they wouldn't know what to do with this. You gave them a fractional answer and good, great, where do I put it?
Right.
It's like a result nobody wants to hear.
Right, which is also the same for your complexes. I mean, where would you put your complexes if you wanted to have them in a fractional dimensional space?
No, so here there is no fractional dimension. In my setup, there is just embedding dimension. It's solid integer. Right?
That's right. Yeah.
So, and it is still semi-fraudulent because you embed in so high dimensional Euclidean space, the true dimension of your manifold, of course, may be lower, right? So this is still not quite the right answer, but it's at least you can estimate where this manifold of smells can be embedded, which is a good start, right? And the true answer would be, okay, find the DEM manifold, but it's very hard.
Okay, so do we have any other questions? Remember to unmute yourself to ask questions. So if not, then I would like to thank Vladimir again. And now I would ask everyone to unmute themselves so that we can clap. Yeah, and thanks so much again for joining us.
Okay, thanks for